All right, welcome everyone to a new installment of the MAG-ROM's seminar. It's a pleasure to introduce today Maxim Olshanskii from the University of Houston. And Maxim will be talking about the tensor POD-ROM for parameter-dependent dynamical systems. So without further ado, Maxim, take it away. Thank you.
All right. Thank you, Ryan, for inviting me, and thank you, and Maria, for organizing this seminar in general. So this is my topic, tensor methods for ROMs. My collaborator, Alex Mamonov from University of Houston. And let me jump directly into problem formulations and my objectives. So we're interested in building ROMs for dynamical system which depends on parameters. So this is my notation for this talk. Alpha is one of key notation is a vector of parameters. It may live in high dimensional space, Rd in general. So U is always a state. M is the form dimension. All right, so if we think about the standard POD-ROM, what we do, we sample parameter from our parameter domain, which is alpha capital, which is a compact set in Rd. We form a snapshot matrix M by N G. G is the number of parameter. We solve for n left singular vectors, and we project. This is how we usually go. This is the standard POD. So a well-known challenge here is that this POD space, it loses the information on parameter dependence in the problem, and in general, it may fail to efficiently represent our states for out of sample parameter values, and or if the Kolmogorov n width of our parameter solution parameter manifold is large, then we may need a quite large quite large basis to represent even in-sample parameter, in-sample states for in-sample parameters efficiently. So well-known challenge, and there were several ways suggested in the literature to address it. So we are trying to do this using tensor technique. So our goal is to have a parameter-specific ROM space to project the system for any incoming parameter out of sample, not necessarily in sample. And then we project our system on this space and do usual stuff. So clearly that we need to do something different here instead of well, standard POD. All right, so here comes the idea of tensorization. So we have, think for a moment that we have a Cartesian grid for parameter sampling in the parameter domain. So my sampling set will be a hat. So whenever you see hat, this is correspond to test, not test, but to learning parameters or to sampling set. Then it's natural to organize snapshots in a tensor, which will be D plus 2 tensor. So we have d directions in the tensor corresponding to each of the parameters. We have space and we have time, so we have this natural tensor structure, and we want to exploit it. So I will always use the first direction in the tensor for the space, last direction for the time variation, and everything in the middle. These are directions in the parameter space. So if we go with the usual POD, then essentially what we do, we unfold this tensor into a large matrix, and then we do SVD. But by unfolding this tensor into a large matrix, we lose any information about the variation of states with respect to any parameter, any explicit information at least. What we want to keep it. Oops, too fast. So how do we want to keep this information? We want, instead of SVD, we want to do low rank tensor decomposition, or approximate low rank tensor decomposition. So think about POD or as a truncated SVD. So then then we can interpret a truncated SVD as finding optimal low rank approximation for the snapshot matrix. Now instead of the matrix we have a snapshot tensor, so we can think about some optimal or quasi-optimal low rank approximation of the snapshot tensor. This is a picture cartoon which illustrates the idea. So just keep this cartoon in mind for the rest of the talk maybe. So this is standard SVD or POD. Now we have a tensor 3D. We have just one parameter, yeah, to illustrate this idea. And this is one of the low rank decomposition of the tensor. There are several approaches how we can do low rank approximation of the tensor. So just illustrate one of them. So you see here we keep this information about the variation of our snapshots in the parameter space, and the name of the game is to use this information to benefit from this information while we build the ROM. All right, so summarizing the general form of our, I call it LRTD, low rank tensor decomposition, or I will say just tensor ROM. A generic tensor ROM is this. So we collect snapshots as usual, and at the end we project our dynamical system into parameter dependent space, also the usual. But in between we now do our dimensional reduction in 2 steps, offline and online. In offline step we will find low rank approximation of a tensor, so model reduction. And in the online stage, we will pass some information from this low rank tensor approximation to the online stage, and based on this information, we find parameter dependent optimal low dimensional ROM space for any incoming parameter. So things to address are at least the following. Which of the low rank tensor formats we want to use. There is tensor rank is ambiguous thing, so there are several of them. And how to build the parameter-dependent ROM space if we have this low-rank tensor approximation for any out-of-sample parameter. So I will start with addressing the second question, because how we do this really doesn't depend on the particular low-rank tensor decomposition that we use. All right, so this is the question I want to address right now. There are several ways how to do this if we have LRTD. And one natural way is to do what we called in-tensor interpolation. So to explain this procedure, I need one useful notation of K-mode tensor vector product. This is essentially a convolution of a tensor with a vector along the kth mode. So it's like the matrix vector multiplication, but along the one particular mode. And as an output, we have a tensor of order m-1, so one order less. So we convolute, we make a convolution of a tensor with a vector along one mode. So this is the operation that I will need. All right, and then one suggestive consideration to understand what we do is the following. Assume for a second in-sample parameter, so parameter from the training set, and let EI be a vector of zeros and one in one particular position, which remembers the position of the ith component from our parameter among the grid nodes, the nodes of the sampling set for the parameter. So all EIs are the vectors of all zeros and one in a particular position. Then if we take a convolution of our tensor, of our maybe tensor in the low rank format with these vectors, then along the parameter direction, as an output, we have m by n matrix, which is the m is space, form space, dimension n is form time dimension. And then if we consider the orthogonal bases in the column space of this matrix, then any state for this particular parameter can be represented in this basis up to with the accuracy of our low rank tensor decomposition. So epsilon, remember, let me go back here. Epsilon is the accuracy of our low rank, of our approximate. We never do this exactly. So it's like a truncated SVD. We are not interested in full SVD. Truncated, here is same. We are not interested in full low rank tensor decomposition, but in some truncated. So and epsilon throughout this talk is how accurate we approximate the tensor in the low rank format. So then we can represent any state up to this epsilon. So summarizing, the information about the parameters for particular state is still in our tensor, in our low rank tensor composition, and we can easily extract it. So we can benefit from this. And we now proceed with using this for any parameter from the parameter domain, not necessary in sample. So how we do this? We now assume alpha to be just any parameter from the parameter domain. And what we essentially want to do, we want to interpolate this parameter, or better to say, we want to interpolate snapshots using the grid in our parameter domain. So we interpolate this parameter using the sampling grid in the parameter domain. So now I capital A is the interpolation procedure, which for any entry from our parameter correspond a vector where ki is the number of sampling points in ith direction, such that we can interpolate any smooth function using the values of a function in our grid in the parameter domain. So, for example, we can use just linear interpolation between the closest point in the parameter domain. In this case, these are obvious formulas. So only two non-zero entries in each vector here, in this space. Or we can do a high order polynomial interpolation, or we can use something else. Our favorite is interpolation of degree 2, so using 3 points. So that's empirically works the best in our examples. So with this interpolation procedure, if we define this interpolation procedure, we can extract and interpolate the information using the LRTD, low rank tensor decomposition, phi tilde, and define now this our alpha specific, parameter specific reduced order model basis that we were looking for, which is now the first n left singular vectors of the following matrix, which is phi tilde alpha, dependent on alpha. To find this matrix, we take the convolution of our tensor in the low rank format over each mode in the parameter space with respect to this interpolation vector. And the remarkable thing that this procedure can be done very quickly and very efficiently in any low rank tensor format that we consider. Oops, wrong direction. So this is one key observation, that if this tensor here is in low rank format, that it turns out that computing SVD of this matrix, so finding this alpha specific basis, is very fast. Very fast means it depends only on tensor ranks, but not on the full order dimensions. That's what makes this approach very efficient. All right, let's try to address the other questions. So again, the notion of the rank format is ambiguous. This is unlike the notion of rank for matrices. So there are several low rank tensor formats on the market. So which one to choose? And the next question, how to practically compute these bases for the given low-rank tensor format. So, well, here are several possible choices of low-rank tensor decompositions. These are not the only one. Those probably most popular, and those that we tried, all of them work. So two classical canonical CP decomposition, high order SVD, which correspond to Tucker decomposition. Another one became pretty popular more recently, which is known as in physics as a matrix product state, and numerical analysis as a tensor train decomposition. So I refer to this review papers and other review papers for more information about them, and other options are available. So essentially, the message here that the choice of the particular tensor decomposition depends on the problem. For example, if we have high order parameter space, then we likely want to go with tensor train decomposition. If we have a very nice separation of variables, then maybe CP decomposition is good. But whatever decomposition we choose, our favorite is currently tensor train. But whatever decomposition we choose, the principles are all the same, and it's very easy to replace one tensor decomposition with another one, and just with some minimal changes in the algorithms. So let me illustrate how we work with tensor train decomposition, but again, same principles will be for other tensor train. So let me pick tensor train decomposition and explain how we compute this alpha-specific reduced order spaces if we have approximate low-rank decomposition of our snapshot tensor. So this is how the tensor train format looks like. Quite a bit of notation. So here use sigmas are vectors, use are vectors of the dimension of form space dimension, v is the time direction, so n is the form discretization in time space. So these are vectors in the parameter space directions. So these vectors, if the index varies, are organized in orthogonal matrices. These vectors are organized in small tensors of order 3 with orthogonal fibers. And these limits for summations are tensor ranks, or in this case, these are TT ranks. So the space, the dimensional reduction is coming from having these ranks relatively small. So now we have offline and online stage of the dimensional reduction. In the offline stage, similar to POD, but now working with a tensor, we are finding high order SVD or tensor low rank decomposition. So we find this phi tilde, this approximation, and for TT format and for Tucker format, for high order SVD, this can be done based on truncated SVD for some unfolded matrix. So the computational costs are the same, or essentially the same as for POD. So same tool. So this is our compression procedure on the offline stage. Now we organize these vectors in a matrix, and we keep this matrix for the offline stage. And this in the middle, these small tensors, these are the information, they keep the information about the variation of states in the parameter space, in the parameter domain. So we keep them for the online stage. So we want to use this information. So these vectors we don't need. So vectors U, these are organized in a matrix, which is an orthogonal matrix. And the column space of this matrix is our, what we call universal reduced space. So, which is a low rank space. So, which is a low dimensional space. The dimension of the space corresponds to the first TT rank, so this R1 tilde, but this first rank can be still rather large because this space keeps the information about snapshots for all times and for all parameters. So this information is there. And in other circumstances, this would be maybe our POD space, but the dimension of the space can be rather large and we want to reduce it further. And now on the online stage, we want to find our alpha specific information within this universal space. So before proceeding to online stage, we project the full order system on this universal space. So this is the first stage of the model reduction. So we project our system on this universal space and we pass this information online. Now, the scope of the online stage is for any incoming alpha, find an alpha specific subspace of this universal space. To do this, we need some computations online, but these computations are done only with objects of low dimensions. So here are some matrices which corresponds to these tensors of dimension 3. So Ci is a matrix which is the convolution of each sigma tensor along the second direction with our interpolation vector, which is a sparse vector, only few non-zero entries. And the dimension of this matrix is small, so the dimensions are tensor ranks. So then we take the product. This is a low dimensional matrix, and this is the result which we need. It's very simple to show it, that the SVD of the convolution of the original big tensor in a low rank format with our interpolation vectors is the SVD of this small matrix multiplied by the matrices U and V, which consists of these vectors in the tensors, U on the left and V on the right. Which means if we find singular vectors of C, we also know singular vectors of these matrices. So, or in other words, by finding singular vectors of C, we find coordinates of our final small reduced order space in this universal reduced order space U. So this is the definition of our local reduced order model space. We take first n is small left singular vectors of C, and this gives us these n left singular vectors are coordinates of our universal basis. Are coordinates of our reduced order basis in the universal reduced space U. So, which means that the whole process of model order reduction looks like following. Okay, this is again our dynamical system. We sample parameters, same as for POD. We choose a desired accuracy, how much information we want to keep doing low rank approximation. Maybe this is 1%, then epsilon is 0.01, or maybe more, like 10 to the minus 3 maybe. This is what we usually do. We find low rank tensor approximation if we choose TT format. This gives us U, these sigmas, V, we don't need V, we keep U offline, we pass these sigmas online, and before going online, we project our system on the range of this U. Then for any incoming alpha, not necessary from the sampling set, not necessary from the training set, we compute SVD of a small matrix, and we double project the system. We project the system for the second time on the first n singular vectors of this small matrix. Then, okay, we solve this system, and this defines our ROM solution trajectory in the alpha-specific subspace of the universal space. All right, just a quick comment here that same ideas, same tensorization technique also applies to hyperreduction technique like discrete empirical interpolation method. So in the same way, we can replace SVD dimensional reduction in DEIM with tensor low rank decomposition, and we have alpha specific hyperreduction spaces, and moreover this enables us to extend the estimates from the original papers Sorensen to out of sample parameters. But I will not talk about details of this right now, but the idea there is the same. We want to do low rank tensor decomposition instead of SVD, just to keep the information about the variation of nonlinear path snapshots for online space, for online computations. All right, a brief comment about the overall complexity. This is just a comparison of different low rank tensor format in terms of some complexity and algorithms. So the offline stage. So high order SVD, TT, they're based on SVD decompositions of some unfolded matrix. If we do go with canonical CP, then we need to do some fixed point iterations based on alternatively square. And this essentially reduces the applicability of this format to rather small ranks and not that many dimensions in the parameter space. But yeah, in some cases, this is also pretty efficient. And if you look carefully into complexity, for example, comparing high order SVD and TT, you see that in high order SVD, we have a products, or we have products here. Here we have products of tensor ranks. So which means if D, the dimension of the parameter space, is large, we have this exponential growth of the complexity, and we don't have this exponential growth in for TT. So if we have high dimensional spaces, probably TT or CP, if we have nice separation of variables, is the way to go. Anyway, now I want to talk a little bit about analysis, but before talking about analysis, let me show you a few examples of how it works. So this is one example, one simple example, a heat equation in such a domain with 4 parameters which parameterize in boundary conditions. So this is a linear problem, linear dynamical system, which depends on 4 parameters. And these are some examples of the tensor ranks. So we have 5 ranks for 4 parameter problems, how they depend on the accuracy of low rank tensor approximation. This is from left to the right. We increase the accuracy, so our rank increasing, but not that much. This compares the second row compares the accuracy of doing tensor-ROM and standard POD. These are the gains. So this is a measure of accuracy for the solutions, how we represent the solutions. So especially for high accurate low rank tensor decomposition, so we have a big gain in the accuracy. But again, this is a simple example of linear problem, depends on 4 parameters. All right, so I'll probably skip this slide. All right, this compares the ROM accuracy of tensor SVD and standard POD for this problem. So the statistic here is the ratio between the error of POD-ROM and the error of tensor-ROM for several formats, and for 2 n's. So we do random sampling of the parameter domain. So we have a lot of outsampled parameters, and these bold figures are the mean gain of doing tensor POD. So, for example, here for TT and reduced order dimension 20, the average gain was more than 100 times. We were more than 100 times more accurate. But the variation was really large. So sometimes we were only 5 times more accurate, but many times we were like much more accurate than that also. All right. Well, this is another example. Again, a linear problem, advection diffusion problem. Now we have 9 parameters, and we parameterize the advection field. So we have advection field going from southwest to northeast somewhere. So this field was parameterized, the source was put here. So we have 9 parameters, and these are an example of tensor ranks for higher order SVD and for tensor train. And because higher order SVD has this exponential dependence on the parameter space D, even our ranks are small, the compression is much worse than the compression of TT. So one really wants to go with probably TT for high dimensional space. And again, for different ROM dimensions, we have a big gain with respect to accuracy compared to POD. Okay, this is a classical example. Now, the linear problem, very simple, but many papers do it. So we also try this 1D. Viscous-Burger equation depends on 2 parameters. One parameter is viscosity. Another is the position of the jump in the initial condition. So, okay, this is just a step. So the position of the step is our second parameter. Again, for example, look into this right figure, which compares form solution with TT-ROM, CP-ROM, and POD. So with POD, we were not getting, we are not recovering our solution any good. With TT-ROM and also with CP-ROM, we are pretty accurate here, and we do tensorization both for the states and for snapshots of the nonlinear terms. So these are our dimensions for ROM space and for DEIM space. All right, let me. Yeah, this is the illustration which explains why this tensorization pace, why it's more accurate than doing just standard POD. So especially in this example, we see the gain of this tensorization for doing DEIM. So this is the illustration of the effective rank versus accuracy. So for tensors, we're gaining accuracy much faster by increasing the rank than for the POD. All right, one more example, 2D Allen-Ken equation, another nonlinear problem. It models the phase separation process in a domain with a transition between order and disorder states. So U is a kind of characteristic function. It should vary between 0 and 1. At 0 in one state, 1 in it's 0 in one phase, 1 in another phase, and there is a smooth and narrow transition region between these phases. So it's nonlinear. So Fu is Dow-Ginsburg potential here. We have 3 parameters. Alpha 1 characterizes the width of the transition region. Alpha 2 here enters nonlinear terms, defines the energy level of pure phases. Alpha 3, it's parameterize our initial condition, how much we have one or another phase in the original region. So TT ranks are here. So, and I have some ranks in bold, and comparing the first TT rank and the last TT rank is a good indication of the gain of the accuracy this tensorization is offering comparing to usual POD. So the first rank, this is the dimension of the universal space, which is the space which approximates all possible states for all parameters and for all times. So that's the dimension we would need in POD to approximate all the states with this accuracy. But when we go alpha specific, when we find alpha specific space, this is the last rank which characterizes our final reduced space, and this how many snapshots, this is how many basis functions we need to gain the same accuracy, but doing alpha specific basis with an alpha specific basis. All right, this is some illustrations. So this how the solution depends on the accuracy of the low rank tensor decomposition. It increases from 10 to the -1 to 10 to the -3, and 10 to the -3 is enough to have a nice solution here. So it's perfectly between 0 and 1, no undershoots, overshoots. So this is the accuracy which we want to use. This is just an illustration how tensor-ROM recovers solution for different parameters. So comparing form and reduced order models, while POD with DIM fails to recover the solution really well. So this is for two in-sample parameters, same picture for two random out-sample parameters. All right, so now I spent a few minutes explaining error analysis because this is the part I really like about doing this tensor POD instead of a standard POD, because it also allows us to move forward with respect to analysis of with respect to error analysis of the ROMs. So this is my setup here. I consider an abstract linear parabolic problem, which depends on parameter. So L is some uniformly in alpha elliptic operator, which is uniformly elliptic and uniformly continuous in alpha. So the form space is a standard finite element space conforming of degree m on quasi-uniform triangulation. Form method is again a standard implicit Euler. And okay, this is the bilinear form which corresponds to this elliptic part of the parabola. So very standard setup. Just think about the heat equation parameterized if you wish. So I need some assumption on the smoothness of how smooth is the problem with respect to the parameter. And I here this assumption is formulated. So essentially, I assume a very smooth dependence on of my operator, and also the same for the right-hand side, a smooth dependence on the parameter, and I have derivatives up to p, and p is the interpolation order in the parameter space. So for the linear interpolation, P is 2. For the quadratic interpolation, which we use, is P is 3, and so on. So I assume smooth dependence of the problem on the parameters. I have Cartesian sampling of the parameter domain, and I have sampling parameter, which is a mesh parameter in the parameter domain. This is delta. So I also need inverse a constant from inverse inequality in the reduced space. So this is again standard for the ROM analysis, but now I need my constant not for the universal space, which is reduced space for all snapshots. I only need it for reduced space for a particular alpha, and then I take the supremum over all alphas in the space domain, and I want it to be bounded. So this constant will enter the analysis. And here the result. I also need one more notation. I consider correlation matrices, L2 in this case, for any specific alpha. So again, these are correlation matrices not for all states, but for the states for a fixed alpha. And I take eigenvalues, some of the eigenvalues starting from some L. L is our reduced order dimension. And I take the supremum over all alpha. So this can be shown to be bounded. And this is the final estimate here. So U is the state for bit alpha. UNL is the tensor-ROM solution at time Tn. L is the reduced order space. So this is the part of the energy norm, and my estimate is universal with respect to parameters. So you see, I take the supremum over all parameters in the parameters domain, not in sample, not training parameters, but by all parameters in the parameter domain. And I have the estimate. So in the estimate, we have, okay, these are our form parameters, delta t, mesh size, and now I have these parameters from the model reduction. Is how accurate my low rank tensor decomposition, how fine is my mesh in the parameter domain, and what is the order of interpolation, and this constant, which is usually very small with respect to all other parameters. It's where I truncate for in my alpha specific space. All right, so you see that there is no notion of n Kolmogorov n width of parameter solution manifold here. So this bound depends not on how fast this and with decays. It rather depends on how smooth is our manifold, parameter manifold of the solutions. All right, and I am coming to the end of my talk. So these are some conclusions. So, okay, there are key ideas which I like to iterate. If you have parameter dependence in your dynamical system, you want to use tensor decompositions in place of SVD, then the model order reduction is two-step, online and offline. There are a lot of benefits of doing that. There are of course, some open topics, and the most important is this first one, this which we're working right now. So as you realize, computing the full tensor of parameters, or the full tensor of states for all parameters is expensive. So we want to have low rank tensor approximation of this tensor without computing the full tensor first, but only randomly sampling it. And there are tools in numerical linear algebra for doing this. These are so-called interpolation or completion methods for computing low rank tensor approximation. How to use them? This is our current topic. And if you want to learn more, there are 3 papers. They are long reads. So because we need to introduce too many notations there to explain things, not too many papers we could refer to for this. But maybe a good idea would be to start reading from the very last papers with error analysis, because it explains the whole idea in some simple language, and then you can look for the details in the first papers. And if you're interested in giving it a try, just ask us for a demo script for MATLAB implementation. But it's really, really simple. If you have POD-ROM implemented, just changing it to tensor POD is a simple update. Okay, thank you.
Thank you very much, Maxim. This was a very nice talk. Thank you. Very clear, straight to the point. Very nice. Now, so I do have some questions, but maybe somebody from the audience has some questions. Please raise your hand or just unmute yourself and ask the question.
Hello.
Yes, Ramon. Absolutely.
Hello. How are you? Good to see you, Maxim.
Okay.
Thank you for the talk. Very nice. So I probably missed something, but when you interpolate in the parametric space, how do you guarantee orthogonality of the bases? I guess you have explained that, but I think I have missed this.
Okay, orthogonality of the bases is guaranteed by the 2 things. Okay, so the universal basis is orthogonal. Okay.
Yes.
This is guaranteed by the
yes. No, that's clear. Yes.
Yeah. Then, after we interpolate, we do SVD of the small matrix.
Okay. So okay. After the interpolation, you do again SVD.
We do again SVD of a very small matrix.
No, I understand. I get it. Yeah, the usual idea in local basis parametric ROM is to when we interpolate from the different bases, we don't use this tensor representation. Is to use the logarithmic map to project to the tangent space, and then the exponential map to project back to the original space. So in your case, you replace that by the second SVD of the little matrix. I understand.
Yeah, this is. I think that's a very different idea. What we do.
No, the idea. No. I agree. The idea is different. But again, my question was, how do you guarantee orthogonality of the bases once you interpolate? And the result is clear. Is that you do this second SVD.
Yeah.
I have, if I may, I have a second question. What would happen if you have a parametric space that does not allow for this tensor decomposition? I mean, for instance, the parameters are related, so they do not belong to a cube, let's say, or a hypercube, but they belong to a domain, a compact domain that cannot be tensorized, so to speak.
So in this, okay, this probably more challenging for this. So what we also tried to do, I didn't cover in this talk. So we can consider the parameter domain in this case as one direction. So we have then, we can sample it in some maybe even random way, this parameter domain, and then we have the tensor of order three-dimensional tensor. We have space direction, we have time direction, and we have the third direction for all parameters. This is probably not that efficient as if we can also tensorize our parameter space, but
it's feasible, yes.
it's feasible, and you can also interpolate in this third parameter space.
Right, I understand. No, I understand. So yes, you put all components of the parameters in a single dimension, so to speak.
Yeah.
Okay, thank you very much. Thank you, Maxim.
Yeah, sure.
Thanks, Ramon. Any other questions for Maxim? If not, maybe I can ask maybe a relative quick one. So on slide 21, I really like the slide on the error analysis side. I think that it was very nice on Maxim. But right, so when you have this, so I'm looking at the estimate, and when you have the C inverse, the constant. So I was wondering, I mean, so maybe I'm just thinking like a POD person, but so so this C inverse is the inverse constant for the inverse estimate in the for the finite element method?
No,
or
of course it's bounded from above by this inverse constant in the finite element method, but yeah, practically I think it's much smaller. So we don't see in experiment the influence. So this is inverse constant in this ROM alpha specifics.
That was my question. It's not about the size, it's about where you consider it. Because I mean, is it fair to say that the ROM space is a subspace of the finite element space?
Yeah.
So in principle, you could do C inverse in the ROM space, and you can also say, oh, but this is a subset, you know, the ROM is a it's part, you know, it has a finite element representation. So then you do a C inverse in the finite element space. We've done something like this for POD. And actually,
go ahead.
Yeah, sorry. So just wanted to say that actually there is a difference between the two, and actually in our experiments, the finite element one, but that's limited. It's a narrow focus. But in our experiments, the C inverse from finite element actually produced better results than the C inverse from the ROM space, which is counterintuitive to me, was a bit counterintuitive. That was just for the clarification. So I just wanted to know what space you considered, the finite element or the ROM space.
Yeah, we consider the ROM space. Yeah.
Okay.
So you probably can go around this if you include the finite time derivatives of the snapshots in your tensor and do this this trick, but we practically don't see why we should include this time derivative of snapshots. So that's why we are not doing this in the analysis. We want to analyze what we use.
Gotcha. Makes sense. Thank you. So any other questions for Maxim? I don't see any raised hands. Maybe we just thank Maxim again for a very nice and fresh type of talk. Thank you, Maxim.
Yeah, thank you, Stride. Thank you, guys.
Very nice. And we'll see everyone next week with the next talk in the NAGROM seminar. Thank you for coming, and once again, see you next week. Thank you.
Thank you.